Hello ladies and gentlemen, and welcome to our second lecture of the unit. In this part of our Unit 4, we'll be talking about electrons in the atom. There are three objectives that relate to this particular section of information. First, we're going to be able to define valence electrons and determine the number of valence electrons for elements using the periodic table. You will draw electron dot structures to illustrate the number of valence electrons in atoms and ions, so there will be a difference between how those look. And we will look and recognize how the number of valence electrons determines what type of ion that will form. Remember that the type of ion could be a positive or a negative ion, and we have terms to describe those. So, as a quick review, in terms of the Bohr model, we talked about the fact that electrons exist in energy levels. Bohr suggested it was like planets orbiting the sun, and we know that part of his model is not correct, but he was very on track with this idea of different energy levels. So we'll see that the higher the energy level of the electron, the further it will be from the nucleus. Within these energy levels, we're going to see that they get more complex as they get larger. The first energy level, like our Bohr models, can only hold 2 electrons. The second energy level is able to hold 8, and then the third energy level holds 18. Remember we said that higher than about 18 electrons we couldn't do Bohr models, and so this is where this is getting a little bit more complex. The fourth energy level can hold up to 32 electrons. Now you might be wondering what keeps those electrons near the nucleus. Remember that the nucleus has a positive charge and electrons are negatively charged. The force of attraction between those opposite charges keeps the electrons near the nucleus. However, if they have higher amounts of energy, they are able to exist further from the nucleus. They can overcome that attraction because of their greater energy. If they have lower energy, they'll be closer to the nucleus. Think of it kind of like movement. They are not going to be moving as fast because they don't have enough energy to get away from the nucleus. Now, valence electrons are the definition, or term I should say, that are given to the electrons that are furthest from the nucleus. If we are drawing a Bohr model, they are the ones in the final ring. Those electrons are going to determine how the atom reacts with other atoms. Think about the fact that atoms bouncing into each other are going to interact because of making this interaction. The outermost electrons are the ones that are actually going to have the opportunity to interact. All the ones in the middle are kind of blocked out by those outer electrons. How many they have will determine whether I make a positive or a negative ion. Now, when we draw dot models, what we are going to be able to represent are those valence electrons. So a dot model will only represent the valence electrons, those outermost ones. When we did the Bohr structures, we did all the electrons in the atom. Here we're going to see only the valence. There are 2 rules that we need to apply. The octet rule applies to pretty much all the atoms except for hydrogen and helium. They are going to react or change, become different to be able to get 8. 8 is considered a full outer energy level. Really small elements like hydrogen and helium can only fit 2 electrons in that energy level because the first energy level, we said, only fits 2 electrons. So hydrogen and helium will have 2 electrons at the most. Any other element that we do can fit up to 8. So if I was going to draw for helium, and I look at the periodic table, I would see that hydrogen is in the first column. Okay, remember we said there's similar characteristics in a column. Because it's in the first column, we see that there's 1 valence electron. So I simply draw a dot to represent the electrons. Now, if you take a look in your note sheet, there are some periodic tables there for you in the right-hand column. You'll see that carbon is in the 4th representative column. Remember 4A, those Roman numerals? Because it's in the fourth column, it has 4 valence electrons. Now when we draw the electrons, we're going to spread them out separately first. So I can't make any pairs before I spread them out on each side. Think that there's like a square around the element, and we have to put sets of 2 on each side. I have to go around and fill in one first before I go back and make any pairs. Fluorine, the last one we're going to do here for this slide, is in 7A. That means there are 7 valence electrons. So I'm going to draw 7 dots. So here we see that there are 7 electrons and 1 open space on this fluorine atom. So the dots represent the valence electrons. The diagram posted here shows the Lewis dot diagrams of these representative elements. You'll notice that in each column, they all have the same number of valence electrons. We said that the number of valence electrons is what determines those shared chemical and physical properties. So you might wonder, how do we know those are the valence electrons? Well, we're able to look at how many we can test for in experimentation, but where this really becomes important is how we form the ions. We said that if an atom gives up electrons or loses them, they are going to become positive because now I have less negative charges than protons. The number of electrons they lose will determine the charge on that ion. Now group 1A, if we look back, we said they have 1 valence electron. Consider that it's going to take energy to take them off. Do you think it would be easier to lose 1 or gain 8? Well, in terms of energy, it's going to be a lot easier to give 1 up than take on 7 to get the total of 8. Sorry, I think I said that wrong initially. So for each group, pretty much up to group 4, it's easier to give up the electrons. It takes less energy to do that than take on what they need to make 8. Once we hit group 5, quick check again, we see all of those have quite a few electrons. So from here on, it's actually easier to take on electrons than give them up. So 5A would gain 3 to make a -3 anion. Group 6A would gain 2, and group 7A would gain 1. These numbers are what give us a total of 8 electrons in that outer shell. Now if you take a quick peek back, those noble gases, they started with 8 to begin with. So they already are stable. They don't need to change or react to get that full outer energy level. That's why the noble gases are generally non-reactive. The last little piece is when we draw dot models, we need a way to represent the ions a little bit differently. So after a neutral atom has become an ion, we draw dot models that can reflect what happened to those ions. So if you recall, the original hydrogen atom had 1 electron and it gave it up. So to show that, what we do is we draw brackets around the element, and then we place the charge and the value of the charge in the upper right. So the fact that there's no electrons or dots around this model is reflecting the fact that they were given up. For any time that I gain an electron, you'll notice that we add in dots to fill in the total of 8. So carbon started with 4, those are the ones in black, and then it gained 4 more in that first example, have a total set of 8. Those are the gray ones. So ion dot models are almost easier than the individual neutral atoms because I'm only going to have none or all 8, except in the example of like helium where you would have 2. The last thing you have to remember is to put the charge on your right-hand top corner. So dot models regular, show the number based on the column. Column 1, I have 1. Column 2, I have 2. and so on. If it's an ion and I gave them up and I became a cation, those will be positive. You show the brackets, no electrons. If we gain electrons and we form an anion, those will be negative. You show all 8 electrons, and you show the charge on the atom. Now your notes has 2 areas that you need to summarize for this set of information. Make sure in that summary section you answer both of the questions.